Yes, hello. Hello, everybody, and welcome to the Chiventa. My name is Franz Lanzerath, and I'm one of the co-founders and managers at TLK Energy. TLK Energy is an engineering company, and we are specialized in modeling and simulation of thermal systems. My talk today is about fast product development with virtual prototyping and hardware in the loop testing. And yeah, here short motivation for this. Yeah, when you classic approach to design a controller, yeah, you start to write the specifications for your controller, and then you program your code, usually in C, and then you put it on the hardware, the controller code, and then you test it with the real machine. Yeah, and yeah, this is a reliable approach, but when there's an error or you want to improve your controller, then this is quite time-consuming and costs a lot of money because you're always in the lab and have to perform a lot of tests, and this costs time and money. So the idea is now to skip some of the tests in the lab and instead use a model to design your controller. Yeah? And there are basically 3 steps you can do without any hardware in the lab, and all starts with a model of your system. Here in this case, I show an example with a heat pump. Yeah, so we have a model of our heat pump, and we want to develop a controller for this. So with this physical model here, you start to develop your code. You think about control algorithms, and you could start to design or write a first control in Simulink, for example. Yeah? And then you can test this controller against your model and perform some tests and improve your code. And this, of course, is really fast because this model does not need to run in real time, but can be run much faster, so you can perform a lot of tests there. When you're happy with this code, the next step could be that you really compile your code or write C code on the basis here of your code that you developed, and then really test the C code again with your model. But this step is often skipped, and you go directly to the hardware. So you implement your code on the hardware controller, and then really combine your hardware controller and test it with your model. Yeah, so here we have the hardware in the loop, and usually this code of the plant model is then simulated on a real-time machine. Yeah, so you can really test the real controller against the real-time machine, and then this is the last test before you really go to the to your system and put or connect the controller to your real system. I will show you the whole procedure, the whole tool chain here on a simple example for a heat pump. And we are looking here at a simple heat pump system for a domestic air-to-water heat pump. And here we have the compressor that takes up the power and compresses our refrigerant. And then here we have the evaporator. The evaporator takes up heat from the ambient, and then the heat pump in the condenser, this heat is delivered to your heating system or domestic hot water system. Yeah. And the problem, or one of the problems for this heat pumps is that in winter, when you have cold and humid ambient, that the evaporator ice can build up on the evaporator, and this, of course, lowers the performance of the system, and then you need to defrost your evaporator. Yeah. And for doing this, there's one possibility that I show here. You can just reverse the cycle. So instead of going with the hot gas through your condenser and condensers there, you can here switch the cycle and then go directly with the hot gas through your evaporator and heat it up and defrost your evaporator. Yeah. And For this example, we want to look at a simple control algorithm that we will develop with the concept, with the model in the loop and hardware in the loop concept. Yeah? And the question is, when do I have to change this operation mode of my heat pump so I have a good performance for the heat pump? Yeah? And of course, you could do this all in the lab with a controller, as I showed, write your C code and do it on the real heat pump, but this, of course, takes a lot of time. So we do this with our model-based controller design. The basis for all this is, of course, you need a model of your plant. Yeah? So without a model, without a reliable model, you can't do this. Yeah? And this is our expertise here of modeling heat pump systems or any kind of thermal systems, but our focus really is on two-phase circuits like heat pumps and air conditioning circuits. So in this case, we have a dynamic system. Yeah? So our plant model must be able to reflect the dynamics of the system. Then we have flow reversal, because when we switch the whole thing here, the whole cycle collapses, and the fluid here in this part of the system, we have flow reversal and also zero mass flows at some point in time. This is really complex to model, but we have a solution for this. We use Modelica as a modeling language, and we have a model library, HiL-testing, that we use for modeling this whole setup here. And when we have these model, first you can start also to write your controller in Modelica and perform some tests. But when it comes to, let's say, when you want to go the whole tool chain, MATLAB Simulink from MathWorks is a good idea to use this and write your controller there, because with MATLAB Simulink you have good possibilities really to export your code later on to the real hardware. Okay, so now let's think about a first controller setup. What could we do? Very simple setup, not very sophisticated. Is we just defrost every 20 minutes, no matter what, So this works, of course, but you can do this. But as you already can see here, we have two cases with different ambient temperatures. These are now simulation results from our model, and this really simple controller that every 20 minutes just starts the defrost operation. And you can see here on the upper part the ice mass on the evaporator, and here you can see the COP of the system. And for ambient temperature 1 degree C, you see that ice builds up, and then here's the defrosting, and the same again. And here you see, the COP is still quite good, and then we have the defrost. It takes a couple of minutes, and then the normal operation starts again. For 7 degree ambient temperature, this is not so good, because we have really a lot of ice here built up, and then at some point the COP goes down because the air can't really go through anymore through the evaporator, and so the whole system, the COP, the performance of the system drops dramatically, and but our controller is not very intelligent, it's not very good, so it waits until 20 minutes and then starts the defrosting cycle. And this is actually too late. So this is a problem with this controller, and of course this is not efficient. You should think about something better. And this is just an example how you can first start with a simple controller and then model it and simulate it and see what happens. And of course, this 20-minute trigger would also work in summer at 35 degrees C, something like this. Okay, so let's think about a little bit more sophisticated control algorithm, and for this we take the we have here defined a value that contains the evaporation capacity, the heat flow at the evaporator, and the difference between the air temperature and the evaporator temperature. So this value contains both the heating or cooling power and the temperature difference, and now the defrosting is triggered when this value drops below a certain value. Yeah? And now you can see what happens with some kind of this controller. You can see here again, we have 2 cases with 7 and 1 degree C. And you can see here, yeah, in this case, when we choose a good value, that at approximately 300 grams, the controller is triggered. The controller triggers the defrosting mode for both scenarios here. Yeah, so this seems to be much better than the old controller. Yeah, so we could now at this point we could say, okay, this is good enough for now. Let's go into let's do the next step and export the model to Simulink and really write the program, the code in Simulink, so that we can later on put it to our hardware. Yeah. So what I showed you right now, we did completely in Modelica, a first prototype of the controller, and now we're going to Simulink. Yeah, because here we really have a great support for code generation that we don't have in Modelica. Okay, so how can we do this? How can we get our plant model to Modelica? And this is actually quite easy because there's a standard called FMI, Functional Mockup Interface. So we can export our whole plant model now without the controller, yeah, just the plant model and interfaces, but not the controller itself. Yeah, and then we export this, and we've got a functional mockup unit. We can directly import again in Simulink. And then we have our plant model here in Simulink. And then we write the controller code here in Simulink. And here, these are just some output values we want to show later on. But basically, here we have the control loop with the controller and the plant model. So we have here again model in the loop for the controller. And Simulink is really good also in performing some standard tests. So you can think about continuous integration for your controller development, that when you have your controller, that you can test it again for different cases. Yeah, and one case, for example, could be that the temperature here at the condenser rises quite strongly because there's a need for domestic hot water, and this might be return flow of the hot water. So you have a step here in the temperature, and when we look here now at our case with the 7 degrees C, you see that here the de-icing is triggered here at approximately 300 grams, in normal operation, and then here when we switch it, it's triggered already, and it's too early, When we have constant operation again, it works fine. But here, for this case, for the switching, it's triggered too early. So now we see again, this is it's not perfect, the controller. We need to think about how to prevent this or just live with this. It could also be an option where you say, it's okay, it's not the best thing, but we can live with it. It's also okay. With this in mind, we now have identified unexpected behavior that we haven't foreseen when we developed our controller. And this is possible with this model in the loop approach, because you can test it against your plant, and see what happens and if this is really a good control strategy. And when this happens at the test bench, or even worse at the customer side or in a field test, this is a really expensive thing. So you don't want to mess with these cases, but it's much easier to handle this when you're still in the development process. So this really could mess up your development schedule, or and cost you a lot of money and time. So in the last step, then, when you really think, now I have improved my controller again, or this is okay, then you can do the next step and go to the hardware. And here it's really nice, because this plant model, what we have as an FMU, can directly export it from Simulink then on a real-time hardware and a real controller. So, and then you can really test the I/O communication of the real controller and test the compiled code, because of course there again unexpected things can happen. And how this is done, I can show you at our booth here. Because I think that model-based control design really is helpful and can save a lot of time, and it's worth to do this. And yeah, with this approach, with model in the loop, software in the loop, hardware in the loop, you have all the development stages for the controller development, and you have a complete tool chain to develop a controller. And I think there's a lot of advantage to have with this. And with the FMI standard, it's easy to develop a plant model in a really good simulation environment and then use it in all the steps, yeah, in Simulink and on the hardware later on. Yes, so if you're interested and want to see how this works and really want to see the hardware set up with the real controller and the hardware, the real-time system, then yeah, please come to our booth. It's in hall number 4 and it's booth number 508A. Thank you very much for your attention.